a curiosity that has intrigued humanity for centuries. What would it be like to find alien life? But where should we start looking? After all, the universe is gigantic, full of infinite possibilities. One clear point is that however exotic alien life may be, it will be subject to the same laws of physics and chemistry that limit us here on Earth. The same laws that affect us affect any other form of life. What's more, each alien environment will impose its own limitations on the types of beings that can evolve there. With trillions of planets out there, each one is like a bubbling cauldron of chemicals, undergoing its own complex evolution. Now, how to organize this diversity? We can divide it into two sections. Life as we know it, which would harbor beings with biochemicals similar to ours. Life as we don't know it, which would harbor beings that challenge our concept of life. Alien life may be more like us than we realize. But what do we have in common with other beings in this world of possibilities? It's carbon. This element is very important in the universe, being able to form large and stable molecules. Carbon is unique because it can bond with other elements in 4 directions and form long, stable chains with itself. This allows it to form complex molecules, which are essential for life. This ability makes carbon the protagonist in the molecular immensity of life. And believe me, the same carbon compounds we know have already been found in distant places, stuck to meteorites and floating in clouds of cosmic dust. They're like little snowflakes, scattering across the universe. Now, what if alien life also chose carbon compounds for its biochemistry? They would have plenty of options, as scientists have already identified more than 1 million alternatives for DNA, all based on carbon. Some scientists suggest that, because of convergent evolution, if conditions on other planets are similar to those on Earth, we could see very familiar forms of life. Characteristics such as vision, echolocation, and flight have evolved independently several times in different species here. This process of convergent evolution could apply to alien planets, where creatures face similar environmental pressures. It's not guaranteed, but it is possible that there are certain universal similarities in life. Each characteristic would be adapted to its local environment. For example, on dimly lit planets, creatures could have large eyes to capture more light, like nocturnal mammals. Some scientists suggest that humanoid organisms could exist on other planets. It seems unlikely, considering the long and complicated chain of events that led to our evolution. But if just 1 in 100 trillion Earth-like planets produced a human form, we could still have thousands of creatures like us out there. Convergent evolution is also common in plant life. Photosynthesis C4, for example, has arisen independently more than 40 times. Would alien plants look like ours or completely different? On Earth, plants appear green because they absorb sunlight, but stars vary in color. Alien plants may evolve different pigments to adapt to their sun. For example, plants around hotter stars could be redder, absorbing blue light. On the other hand, around red dwarf stars, the vegetation could be black, absorbing all wavelengths of light. Because of a pigment called retinol, a precursor of chlorophyll, it reflects purple light. So if this pigment called retinol was predominant, then the Earth could have had a purple appearance. But what can happen when we change the length of a planet's day, or when we change the inclination? What if we change the shape of a planet's orbit or its gravity? Perhaps it would be planets with long elliptical orbits, where the seasons would be extremely drastic. Now, the most curious thing is that there may be worlds that seem dead for thousands of years, and then suddenly come to life. We know that most of the rocky planets discovered so far are massive super-Earths. But how would life evolve on these worlds? In the seas, gravity doesn't matter so much because the water helps us to float, just as we float when we're relaxing in the pool. This is because our bodies have a density similar to that of water. But when we get out of the water and onto dry land, we really feel gravity because then we no longer have the water to help us float. A high-gravity planet isn't high gravity everywhere. If you're in the sea, where all life begins, there's almost no gravity, because we're very similar in density to the material around us. It's the same with animals. When they're in the sea, they float easily, but when they go to land, they feel the weight of their bodies due to gravity. High G-forces would require large bones and muscle mass in complex life on Earth, as well as a more robust circulatory system. Plant life, on the other hand, would be hampered by the energy cost of transporting nutrients under stronger gravity. On the other hand, low-gravity planets would more easily lose their atmospheres to space and wouldn't have a magnetic field to protect themselves from cosmic rays. But what if these smaller worlds harbored secret oases, like huge cave systems that provide refuge for life? The smallest possible habitable planets are estimated at 2.5% of the Earth's mass. And if life evolves on these worlds, it could be an impressive sight. Plant life could grow to dizzying heights, able to transport nutrients higher in less gravity. Without bulky skeletons and muscle mass, animals could have body types that defy imagination. Here on Earth, it took 3 billion years for evolution to produce complex plants and animals. Simpler organisms are more resistant, adaptable, and widespread, as in the case of microbes. But even finding the smallest alien microbe would be an incredible discovery. Like stromatolites on Earth, bite-sized life can leave a big footprint. Layers of microbes could accumulate on large rocky mounds over time, leaving behind spooky structures. Stromatolites are considered living fossils and provide evidence of some of the oldest life forms on Earth. And in large enough numbers, some alien bacteria could leave a distinct biosignal by exhaling gases that would not naturally coexist, such as oxygen and methane. A biosignal, or biosignature, is an indicator or set of indicators that suggest the presence of life. These signs can be chemical substances, patterns, structures, or phenomena that are associated with biological processes. In the context of this phrase, a biosignature refers to a gas or a combination of gases that would indicate biological activity, such as the presence of oxygen and methane together, which is an indication of biological processes at work, since these gases do not naturally coexist without the influence of living beings. Now let's talk about something surprising. The nearest Sun-like star that harbors an Earth-like exoplanet in the habitable zone is only 20 light-years away. And best of all, most brown dwarfs are too hot to support life as we know it, but some have the perfect temperature. Inside these brown dwarfs, there are essential elements for life in their atmospheres. Now imagine this. In the middle of the clouds of these stars, there are layers with the ideal temperature and pressure for habitability. But this leads us to an intriguing question. Aren't we looking in the wrong places? What if nature is more creative than we think? Most of the universe is either too cold or too hot for liquid water and the biochemistry that sustains life as we know it. But if we're wrong, we should broaden our horizons and look for life in unexpected places. And while no element is as versatile as carbon, silicon is an interesting candidate. At first glance, silicon looks similar to carbon. It forms the same bonds in 4 directions and is abundant in the universe. However, silicon bonds are weaker and less likely to form large, complex molecules. Even so, they can withstand a wider range of temperatures, which opens up fascinating possibilities. Life based on silicon, rather than carbon, would be more resistant to extreme cold, offering a whole new range of strange forms. The problem is that, in the presence of oxygen, silicon turns into solid rock. So silicon-containing beings would need to live in oxygen-free environments, such as Titan, Saturn's icy moon. Its vast lakes of liquid methane and ethane could be perfect for life based on silicon or other radical biochemicals. Without sufficient sunlight, beings on worlds like Titan would be chemosynthetic, obtaining energy from rocks. These life forms could have very slow metabolisms, with life cycles lasting millions of years. At high temperatures, silicon-oxygen bonds become more flexible, allowing for more dynamic chemistry. This has led to an incredible idea: silicon-based life forms living inside molten rock. If so, aliens could be under our feet, deep within the Earth, in magma chambers, as part of a hidden biosphere. Dust clouds and empty space seem like unlikely places to find something alive, don't they? But something extraordinary happens when cosmic dust meets plasma, which is a type of ionized gas. In simulated experiments, dust particles spontaneously organize themselves into helical structures reminiscent of DNA. And amazingly, these plasma crystals began to exhibit behaviors similar to those of life, replicating, evolving into more stable forms and transmitting information. Plasma is the most common state of matter in the universe. If these complex evolving crystals really exist, and if they can be considered life, then perhaps they are the most common form of life in the universe. When massive stars explode, some turn into super dense cores called neutron stars. It's as if they were huge masses of atomic nuclei squeezed together like sardines. On the surface of these stars, the conditions are impressive. Gravity is 100 billion times stronger than on Earth. But beneath this crust of iron nuclei lies something intriguing: a hot, dense sea of neutrons and subatomic particles. These nuclei, without their layers of electrons, obey completely different chemical laws based on the strong nuclear force that binds the nuclei together. In theory, these particles could come together to form larger macronuclei, which could then combine into even larger supernuclei. Now, get ready for the unexpected. In this surreal environment, it is possible that these basic conditions mimic the conditions for life. Heavy molecules of nucleons floating in an ocean of complex particles. Does life need to evolve naturally, or can it be designed? And if intelligence enters the equation, what then? Without traditional biological limitations, synthetic life and machine-based life could come out ahead. They can thrive almost anywhere, even in the vacuum of space, opening up immense frontiers that biological organisms could never explore. And unlike slow natural selection, technological evolution is advancing at an exponential rate. Did you know that self-replicating machines could colonize an entire galaxy in just 1 million years? But how would hyper-intelligent life organize itself? We can't predict that. But convergent evolution could be at work. Silicon, for example, with its electrical properties, could be the universal basis for machine intelligence, overcoming our biological limitations. As the universe ages, machine intelligence could dominate, and natural biological life would become just a curious starting point. We could lead this transition, becoming the first link in an intergalactic chain of life. Quite an experiment, don't you think? Loren Eiseley said that we only meet when we see the reflection of a non-human eye. Could that eye one day belong to an intelligent alien? The sooner we let go of our limited view of evolution, the sooner we can explore our origins and our ultimate destinies. So, what do you think? Will we ever find an alien eye that makes us think?